Most engineering teams operate under a hidden assumption. They treat software architecture as a flat collection of text files. When a developer needs to understand how a codebase is wired together, they usually reach for standard Unix tools like grep or find, running broad keyword searches across the repository. But in a language like Go, software relies on distinct structural features that a simple string matching algorithm cannot resolve. Take Go's implicit interfaces. A struct satisfies an interface by implementing its methods. There is no implements keyword. The same applies to wrapped error chains. Specific errors are masked inside string formatting, completely erasing their origin from a basic text scan. To map these implicit connections using text tools, you have to ingest thousands of lines of raw source code just to find a single method caller. That means reading through a massive volume of noise. Active logic is pulled in, alongside inactive mock files, leftover test fixtures, and markdown comments. Sifting through that clutter manually guarantees critical omissions. It is incredibly easy to miss a crucial dependency when it is buried in irrelevant search returns. Relying on text heuristics to navigate a modern, implicitly linked architecture is a broken methodology. For human engineers attempting a package-level refactor, this noise creates immediate operational friction, forcing them to manually cross-reference dozens of files. But the true victims of this architectural blindness are AI coding agents. Modern LLMs are strictly constrained by their context windows. Forcing an agent to read massive text dumps rapidly burns through thousands of tokens and inflates API costs. More importantly, feeding a model this highly unstructured, noisy data directly degrades its reasoning, causing it to hallucinate architectural relationships that do not exist. True codebase comprehension requires us to abandon these broad text searches in favor of a strict, structural ground truth. To safely refactor a repository, we have to translate those raw files into a persistent, structural call graph. This begins by parsing the entire repository via the standard abstract syntax tree in a matter of milliseconds. This process ignores the raw text entirely. Instead, it extracts specific architectural shapes. Once extracted, these structural nodes are mapped together deterministically. Because this is an in-memory structural map, it inherently filters out the noise. Dead code, comments, and unused strings are left behind. What remains are highly actionable insights, active call edges, precise struct mutations, and mapped HTTP route patterns. Through AST parsing, the codebase transforms from a chaotic folder of text into a pristine, queryable mathematical graph. This graph becomes critical during the highest risk operations in Go architectures, splitting, merging, or refactoring at the package level. The mandatory first step for any package refactor is discovering exactly which external consumers rely on your target. To do this, we apply a core mathematical concept, package stability. Stability is calculated using two metrics. First, we measure external consumption, or fan-in. Then we measure external dependencies, or fan-out. We then run these numbers through a specific instability equation. A high fan-in score signifies that a package is heavily consumed by other components in the system. That heavy external consumption makes the package a highly stable structural anchor. It is dangerous to modify because any change will ripple outward. Graph-based dependency queries map every single external importing package instantly. You no longer have to track these connections manually. Package-level stability is a calculable mathematical metric. It eliminates reliance on developer intuition. We are replacing the old method of sequential textual guessing with safe graph traversal refactoring. Suppose a developer needs to modify the signature of a central public API function. Instead of searching for the function name and hoping to catch every instance, the graph immediately computes the transitive closure of the call path. This impact plan traverses the structural architecture up to 3 levels deep. The output is a deterministic checklist. It isolates the exact affected callers, the triggered database transactions, and the specific test suites that will require updating. By extracting these package signatures with all implementation bodies stripped out, architects can continuously audit the global API surface without reading the underlying logic. Utilizing a structural impact plan ensures the exact blast radius of a change is known before a single line of code is ever edited. This level of precision is exactly what AI coding agents require. To function reliably, they need strict context gating. Agents access this massive 3D architecture graph through the Model Context Protocol, or MCP. When an agent queries the MCP server, it prunes the massive graph into highly targeted minimal data packets. In production data, AI agents relying on standard Unix tools suffered a measured hallucination rate of approximately 12%. This chart shows the dramatic difference in accuracy. When agents were fed AST-accurate call graphs and pruned context, the hallucination rate dropped to exactly 2%. This minimal footprint also yields massive secondary benefits. It reduces token consumption, lowers prompt costs, and cuts down processing latency. The end result is a perfectly mapped, secure repository where every single architectural relationship is treated as a completely known, deterministic quantity. Whether you are a human platform architect or managing an AI agent swarm, deterministic engineering requires abandoning text heuristics and graphing the system.